Broadcast is now starting. All attendees are in listen-only mode.
Welcome to Achieving the Best Thermal Imaging Performance for Unmanned Airborne Systems per Unit Gram, Volume, Watt, and Dollar, a webinar presented by Sierra Olympic Technologies and hosted by Photonics Media. My name is Robin Riley, and I am the Photonics Media web editor. Our speaker today is Chris Johnston, President of Sierra Olympic. Chris will be speaking today on thermal imaging camera engines for airborne imaging in unmanned aircraft vehicles. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after this presentation. We encourage you to ask questions throughout Chris's presentation. Just type your question in the question box to the right of your screen, and we will answer as many as possible at the end of the session. And with that, I would like to turn the presentation over to our speaker, Chris Johnston. Welcome, Chris.
Thank you, Robin. Is my screen now visible?
Yes, it's perfect. Perfect right now.
Well, again, thank you, Robin. My name is Chris Johnston. I'm the president of Sierra Olympic Technologies. I'll be honest, I'm used to presentations in front of an audience or in a boardroom or something, but here I am talking to my computer screen, so forgive me if this seems strange to me. I hope it's okay for you. What I'm going to talk about is our experience with achieving the best thermal imaging performance per unit gram, volume, watt, and perhaps dollar in airborne imaging systems. A quick summary of what I expect to talk about, a bit about Sierra Olympic and why we can speak to this topic, infrared camera basics. I'm not going to throw too many acronyms, certainly no calculations or anything at you. Some basics about airborne imaging so you understand terminology and goals and requirements. Sensor system considerations, optical considerations, integration considerations, some examples of some stabilized airborne systems that we've addressed, some development examples, and then kind of a summary of my view of state-of-the-art versus state-of-the-shelf and the challenges of thermal imaging in airborne payloads and development cycles. So a little bit about me. I'm the president of Sierra Olympic. I started in infrared imaging in 1988, came from a background in visible imaging, scientific visible imaging, and then quickly came into a very young industry back then in 1988 in thermal imaging, and started with the very first commercially available indium antimonide cooled arrays. These were 128 by 128 arrays in large liquid nitrogen dewars, and it was a miracle technology back there in the late 80s. Experience with, of course, the INSBE arrays, the platinum silicide arrays, BST arrays. All of those, platinum silicide and BST, are now kind of extinct, in fact. And then the very first uncooled microbolometer arrays, or VOX arrays. And we've been dealing with airborne imaging since about 2001. I certainly had some experience with airborne imaging, just selling cameras, but really started getting into the design issue of cameras and airborne imaging in the early 2000s. And it's been a focus ever since then. And most recently, I summed up our experience in that we've been a launch customer, meaning serial number 1, in 6 high operating temperature midwave systems. That's a little arcane, but hopefully it'll become clear after as we go into this presentation. But we've constantly been on the edge of technology in many infrared imaging technologies. And I want to emphasize that we have a unique position in that Sierra Olympic is a small, unknown company. We're still private. We're not a Raytheon or a Lockheed Martin or a Boeing or an L3, but those are all our suppliers. And we have a unique position in that we get to see all the technology, and we have consistent volume, so that most of the vendors will offer the latest technology to us first, and in order to get it deployed as fast as possible. And that's a position that we've developed over the years. The company Sierra Olympic was founded in 1995. We're currently 20 employees. Most of them are engineers. We're in Hood River, Oregon. Like I said, first sensors for airborne in about 2001. We've supplied over 3,000 uncooled long-wave systems and over 2,500 mid-wave systems. These are cooled mid-wave systems. And that's been our emphasis for the past 10 years. The 3,000 long-wave systems were all shipped probably prior to 2008. And since 2008, we've been shipping primarily cooled mid-wave systems. And we do development, not so much development on the sensors, but integrated sensor systems. Certainly optics, certainly difficult optics like windows, and then we dabble in some laser systems. And you can see on the picture, I threw up a couple pictures of Hood River. We're a small agriculture town in Oregon, about 50 miles from Portland. Top picture is looking south at Mount Hood. The bottom picture is looking north at Mount Adams. So we are truly in the Cascade Mountains in Oregon. We're part of a bigger group. I call it the Hood Tech family. And Hood Tech Corp Vision is our main customer, and they're actually a developer of 2-axis and 4-axis stabilized payloads. And you'll see a bunch of examples of their payloads as the presentation goes on. Sierra Olympic is part of the group, of course. We do the thermal imagers, and thermal imagers are typically the most expensive and heaviest part of a payload, so we have to have special focus there. Part of the group also is Hood Tech Mechanical Corp, or Hood Tech Corp Mechanical, and they make launchers for UAVs. A couple examples are in the bottom, and you can see a catapult launcher on the left and a new development, which is a heavy lift multi-rotor launcher, actually to lift an aircraft and launch the aircraft. It also behaves as a recovery tool as well. So we have experience with, the multi-rotor development market as well. And then another part of the company, and actually it was the way the company started, is called Hood Technology Corporation, and it's very specialized vibration measurement and data logging services. And they have business around the world in power plants and jet engine sites. And when it comes down to it, the development of a payload, an imaging payload, has a lot to do with vibration knowledge and vibration isolation. So all these technologies kind of bounce off each other. So I don't know anything about the audience, so I can be very basic or very complex, but I'm going to try to cover a few very fundamental concepts and define mostly my thinking of basic concepts. So let's talk about infrared. You see the visible light, what our eyes see between 0.4 and 0.7 microns. Those are the colors, violet or blue through violet. You've seen your rainbows, and that's what our eyeballs see. And I call that the visible spectrum. I call near infrared the 700 to 1000 nanometer or 0.7 to 1.0 micron waveband. We have lots of experience with SWIR. SWIR is typically 0.9 to 1.7 microns or 0.9 to 2.5 microns. Midwave imaging systems, you'll hear me say that a lot, MWIR, midwave, that's basically 3 microns to 5 microns or 3,000 nanometers to 5,000 nanometers. And then there's long wave imaging, and I chunk that into 8 to 12 microns. Others call it 7 to 13 microns. But nice little graphic there. It kind of matches what I say. I'd never say, I don't think there's any long wave systems that we deal with that go out to 15 microns. But, and midwave basically is 3 to 5 microns because the atmosphere cuts off beyond that 5 micron wave band and functionally turns back on at about 7.5 microns. So there's a bit of a difference between what the classical electronic or electromagnetic spectrum defines and what is practical in imaging systems. And so this is what I've listed above is practical in imaging systems that you can actually buy. Another important concept here is for thermal imaging is Planck's black body curve. You know, everything emits photons all the time. You can't turn it off. It has something to do with emissivity. I'm not going to go into emissivity at all. I don't want to make this into a fundamentals of infrared imaging discussion. The point I want to make here is that you'll see on the curve on the left, the 307 Kelvin, that's slightly above room temperature. And you can see the peak spectral radiant emittance is at about 10 microns. And that lines up with the long wave infrared spectrum. And that's repeated over on the right, as you can see, the spectral radiant emittance at 10 microns for a 31 Celsius and a 37 Celsius black body. And then if you can, with your mind's eye, translate the wavelength range down to 3 to 5, the 3 to 5 lies on that slope on the left side of that curve. An important issue to take away from here is contrast. Contrast is the derivative of this curve, meaning dQd wavelength, and the long wavelength has less contrast per unit change in temperature versus the midwave, which has a contrast advantage because it's on that curve, on that sloping part of the curve. So what is real in the world and what can you buy that lines up with these, with the wavelengths that you want to detect? So visible is easy. Visible and near infrared are easy. It's basically silicon, and the sensor in your cell phone that you take your beautiful pictures with is a silicon CMOS detector. It's, you know, they produce millions a day. It's a very mature technology. Pixel sizes are small. They're a few dollars. It's inexpensive. Lots and lots of development go into this technology for the consumer and the professional markets. You know, millions and millions of silicon devices are produced each day, whereas the infrared world, you know, if you stretch, you can get 1 million units per year. So the scales are just entirely different, and that's why the visible world, the imaging world that our eyes see, has so much variety and rapid change, and it's just full of options. And as you go down this list, things get harder and harder because the materials are different, they're expensive, and the optics that you have to use are entirely different from what you have in the visible world. So the SWIR, next one down, is I call it just 0.9 to 1.7 for simplicity, and that's dominated by indium gallium arsenide focal planes, in-gas focal planes. You can get more red sensitivity. Some mercury cadmium telluride arrays are available out to 2, maybe 2.2, or maybe even 2.5 now in a linear array. And those tend to be very specialized. And they're still cooled at that. Next is midwave, 3 to 5 microns. Some of the detection materials, or the most common materials now, are indium antimonide, mercury cadmium telluride, and T2SL stands for type 2 superlattice. It's a new superlattice material. I don't want to get too much in the chemistry there. I'll probably make a mistake. But the bottom line is T2SL can offer infrared sensitivity at higher temperatures. And as temperatures go up, your cooler size goes down and you save grams. That's the bottom line there. I should have put this on the view graph after thinking about it. The indium antimonide has to operate at 80 Kelvin. Some of them get up to maybe 90 Kelvin. Mercury cadmium telluride, I think they're up to maybe 100, 120 Kelvin. Type 2 superlattice is up to about 150 millikelvin or 150 Kelvin operating temperature in some cases. So the type 2 superlattice is barreling forward, and I think is going to be the dominant material for the future. And it's a material that we've been invested in for, I don't know, the past half dozen years. Long wave is mature, it dominates the market, and it's dominated by uncooled vanadium oxide. That VOX stands for vanadium oxide microbolometers and amorphous silicon microbolometers. Hundreds of thousands of uncooled microbolometers are sold every year. They're the dominant sensor for infrared imaging. If you have specialized applications that need the sensitivity of a cooled sensor, you can get long wave sensitivity in type 2 superlattice and in mercury cadmium telluride. Those are very rare and specialized applications. But the uncooled market is practically 99, 98% of the sensors shipped per year. It just dominates the infrared imaging market, and it's mostly because the performance is so good, so high, and they don't require cooler, very simply. Some basic concepts I'll go through here with pictures. Most detector arrays can be thought of as a detector, a readout multiplexer, which is a circuit that goes under it, that wires onto, that you get the signal out of. And everything's proportional. Everything's proportional to incoming radiation. In the case of cooled sensors and the indium antimonides and type 2 superlattices, it's a quantum detector. It detects photons, converts its charge to electrons. And then we read out those electrons proportional to some kind of charge. In the case of a microbolometer, I don't have a graphic on this, but it detects watts. You get a little pixel and it actually heats up and cools down. And that heating is proportional to some resistance that can be measured, and it eventually is read out by a readout circuit as well. But the fundamental of infrared imaging is a sensor with an array of X by Y pixels and an optic that focuses the light and then electronics to read it out. It's not that different than the camera in your cell phone. It's just that in the infrared world, we have very complicated sensors and optics. First of all, with the optics, in the long wave, typical optics are all made out of germanium. And in the mid wave, it's germanium, silicon, and other materials. And that is not fused silica or BK7 glass. So you have to deal with these exotic optic materials. Some pictures here, a cooled system in the upper right, that big long tube there is a compressor. It's like a compressor in your refrigerator. And it has a transfer line that loops around back, and it actually cools a sensor that's housed in a vacuum environment behind that window which is that little window on that cone to the left. So in a cooled system, you can call it an IDCA, an integrated doer cooler system, or an integrated or a split linear dual cooler system. The one on the top is a split linear system. The one on the bottom is an integrated doer cooler assembly. And what you see on the bottom is a rotary motor that drives a transmission below it, and there's a displacer that's moving inside that cylinder behind the doer, and everything goes by the Stirling cycle. It compresses helium, and then the helium decompresses and cools, and you have to remove that heat with that helium. And all of this is with the goal of taking a sensor down to 80 Kelvin or 150 Kelvin, depending upon the type of material. So that's the complexity of a cooled midwave system. You have these refrigerators, they're heavy, they're complicated, they're expensive, that have to cool these sensors down to extremely low temperatures. In the middle there, that's a little picture on our bench of a typical uncooled system. So you can see how small and tiny it is. You're not looking at the sensor per se, but you're looking at a window in front of the sensor. This one happens to be a vacuum package sensor, but basically it's just a sensor sitting on top of some electronics, more akin to what you see with a visible sensor, meaning no cooler. So clearly the uncooled sensors are going to be smaller, the cooled sensors are going to be bigger and heavier. Here's an extreme example: cooled sensor on top, uncooled sensor on the bottom. Just night and day in terms of complexity and size. Now, the cooled unfairly is 825 millimeters. The uncooled is 19 millimeters. But just to get a sense of the type of systems that we've been developing and we touch every day. Now, in this world of airborne systems, the item that dominates our work is the optical F number, because the F number drives the size of the optic, and the optic drives the weight of a system. And you have to have a handle on F number before you ever start designing a system. So F number simply is focal length divided by the diameter. And another important issue you need to understand is that uncooled sensors require very low F numbers, or very large diameter optics, very simply put. The maximum F number that anyone should practically use is f1.6, and it's remarkable how the performance of an uncooled sensor will change going from f1.6 to f1.0 to f1.2 to f1.0. So small changes in F number drive the performance of an uncooled sensor. And another thing I want to point out is the NETD of an uncooled sensor is going to be strongly dependent on the F number. NETD, noise equivalent temperature difference, common specification in infrared systems. Most vendors normalize to f1.0. Most optics are f1.2, 1.0, 1.1, 1.3. So you should always, it's sometimes confusing to understand if you're getting that NETD spec off the data sheet when you buy a system that actually comes with an f1.2 lens. So just some examples. Consider an f1.4 100 millimeter focal length. The diameter of the front element calculates out to 71 millimeters. Now practically, in such a design, you wouldn't expect to have a housing that's 71 millimeters in diameter. You have to have points to grip the optic and everything else, and then you have to have you have to take care of temperatures or expansion due to temperatures. So you can't really say that my optical system, if I'm at f1.4 and 100 millimeters, is going to be exactly 71 millimeters. It may be 80 millimeters, but that has to do with just holding the lens. So the bottom line is that when we're dealing with these low f numbers, you're dealing with large diameter, you're dealing with large diameter optics. To expand on that example, f4 with a 100 millimeter optic, again, we're at 100 millimeters, that's down to a 1-inch diameter, so much smaller. And the message here is that in airborne systems, the weight of your optic is probably the main weight that you're dealing with in an airborne system. And so that goes to f number, it goes to focal length, and you have to consider all these overlaid on the weight budget that you have from your aircraft when considering the development of a infrared system for airborne imaging. I like this little graphic on the bottom right. And understand that's an example of the aperture size, all of them being the same focal length. So you can see how tiny you get as your f number goes down. There are costs when you sacrifice f number, though, in many cases. Insensitivity. Okay, so basic concepts in infrared for airborne. And the question you got to ask is cooled or uncooled? The first thing you have to understand is the application in the aircraft. How much can your aircraft lift? Many aircrafts can't even consider midwave because they don't have the lift capacity. They just can't get it off the ground. If your airplane can't fly, then what good is the imaging system? So do I want a wide area? Am I surveying, the county, or am I looking down at a person? Those are fundamental issues related to field of view, usually scaled to horizontal field of view. And then the other half of it is resolution. Resolution, you'll see in an upcoming graph, is what ground sample distance one pixel can generate. And that's a geometric calculation between focal length and pixel size. Now, if you're pushing it and you're doing your best to optimize the focal length, getting as narrow as you can get, oftentimes you're running up against duration. So sometimes we hear that, well, I can handle the extra 10 grams, but all of a sudden my duration goes down by 40 minutes. And that's probably the fundamental issue that has to be considered by the aircraft operator. Is what is the duration scaled to the weight, which is scaled to the primarily the optic on the thermal imager. That's been our experience. So in general, wide field of view will favor uncooled because you don't need long focal lengths. And a 19 millimeter optic is still very tiny and lightweight. Narrow field of view applications generally favor cooled applications. And that kind of goes to the military, which is interested in surveying human scale activity from greater distances. And so they need narrower and narrower fields of view. And we find that the only way we can achieve that is with cooled. Other issues are spectral considerations, what wavelengths do you want to look at? Optical considerations, do you need continuous zoom? Can you live with stepped field of view changes? And then data considerations will always come into play. What is the format of the video you need to generate off an infrared system? Sometimes you have to, how many wires will the infrared imaging system require to transmit data? That's an important consideration. And then I use SWaP-C very infrequently. SWaP-C, of course, stands for size, weight, and power and cost. In our experience, you know, it's mostly weight that takes priority, then size, and then power and cost are kind of a toss-up. Certainly, we can't have extremely power-hungry systems, but most systems fall within a power budget that we have. So here's what we do when we're considering an airborne imaging system. So distance from the ground, AGL, that's how high the aircraft has to fly. And in our experience, at least in the military, it's how high the aircraft has to fly in order to be covert, so that people can't hear it and they don't know that the aircraft is there. Now, you're projecting a focal plane's image onto the ground, and that's the image footprint, and that's at a slant range. It's rare that a camera ever looks straight down, but often it's looking at an angle, and that's called the slant range. And then in imaging, the extent of 1 pixel is called instantaneous field of view, or IFOV. It's usually measured in milliradians. If you know the distance to the target, you can calculate a ground sample distance, a GSD. And then other things that come along with a system are, you know, what do you do with the data? Do you record it on the camera, or do you transmit it as full motion video to the ground? As far as the specifications and the requirements of the system, there are target factors. It's NIRS or GSD. If it's daylight only, if you're only operating during the daylight, you don't need an infrared camera. If you're operating during the nighttime, typically there is a daylight camera. And if you cross day to night, you need both. The other issue is articulation. You know, how much articulation and stabilization do you need? Typically, you need stabilization, more stabilization the narrower you go. And we've been dealing with narrow field of view and 4-axis stabilized systems for many years now. And the wider your field of view, if you're doing wide field of view, your stabilization is lower because your pixels are much bigger and hopefully your vibration isn't that great. As you go narrower and narrower, the relative ratio between vibration effect and IFOV gets greater and greater, and the requirement for stabilization gets higher and higher. Some pictures of drones. So I'm classifying airborne systems into 3 kind of categories. The first, since we're talking about drones, are the multi-rotors. You know, multi-rotors are taking off like wildfire. There's tons of activity in this realm, and it's the miracle that we can just get thermal imagers into the air on these low-cost air vehicles that is a big growing industry. And an example of that is to the left. I think I picked this off, you know, the internet. I think it's a FLIR system, and that has 2 systems. Actually, it looks like there's 3 cameras on there. But the multi-rotor market, just as an example, is just a wonderful market. But there are going to be limitations. They can't lift very much, and they don't have long duration. The middle is what I call STUAS, for small tactical unmanned aircraft. And these are the kind of systems that fly for 24-hour missions, and typically missions at 2,000 meters above ground, where they're inaudible and undetectable by humans, and able to surveil very wide areas and offer full motion video back to a ground station. And this is the area where we have the most experience, is in this small tactical unmanned airborne system market. And then other airborne systems are not so weight dependent. They're on large aircraft. that, of course, on the right is the Predator. I picked this off, you can just Google pictures on the Predator. The payload is that big round thing you see under the nose. And the Predator is about the size of a Cessna, and it flies around for many hours. It has the most hours in any unmanned application, and it can carry payloads that weigh up to 100 pounds or so. Certainly, they have limits. You can't just throw everything onto these aircraft, but they're dealing with 10-pound increments, whereas in the small tactical, in the STUAS market, we're dealing with individual grams or tens of grams per payload. A rule of thumb when we started in the industry was that 1 gram of weight in the payload translated into 10 minutes of duration. So it's not that extreme right now, but just think about how crucial every gram mattered at that point, where if we added 2 grams, you had 20 minutes less duration. That was pretty significant back then. Quickly, here's airborne payloads. We're talking about payloads. So examples of payloads. The ones on the left are typical payloads that go on a multi-rotor. And again, these multi-rotors are beautiful systems. That payload down in the lower left, you can hold between your thumb and your index finger. I think the diameter of the circle is maybe 2.5 inches. Beautiful little payload. The middle column is an example of payloads that are used in the STUAS market. And then on the right, those are the big payloads, the 100-pounders, 50 to 100-pounders. Those are the ones that are used on large unmanned vehicles, the size of a Cessna or larger, or manned aircraft. And I should caveat right now that we don't have too much experience with the manned aircraft market. And I only can observe the multi-rotor market because we don't play in there. But it's that middle row being the STUAS market, the small tactical unmanned aircraft systems, airborne systems market that we have the most experience. Okay, so some infrared sensor basics. This isn't infrared science, this is infrared sensors. So we talk about long wave, mid wave, and SWIR. So long wave is uncooled. There's no cooler. It's small. It can be very lightweight depending on optics. They're relatively low cost. They still seem expensive to visible sensor people, but they're low cost general in the imaging world. And then the optics are generally f1 to f1.5. And in midwave, these are higher performance systems. These are for narrower fields of view. That's a picture on the bottom. You can see the size of a midwave system. And these are typically f4 and f5.5. And these have slant ranges of 2,000 meters or greater. More about F number. This is an uncooled system on the right with an F number of 1.5 versus a cooled system with an F number of 5.5. And those two have very similar horizontal fields of view. The one on the right is 1.5 degrees. The one on the left is 2 degrees. So notionally the same. I shouldn't say that. They're similar, but you can see the size difference. The one on the right is 10 kilograms. The one on the left is 1.5 kilograms. So you're never going to fly that 10 kilogram payload, but you can fly that 1.5 kilogram payload on the left. Therefore, you would default to cooled. Now, let's talk about long wave. Again, long wave is a big business. It's fixed field of view generally. It's used in the multi-rotor market. And it's basically sensor and optic. You can see 3 different optics here. All of these are 17 micron sensors. Top to bottom, you have a 9-degree horizontal field of view, an 18-degree, and a 70-degree horizontal field of view. And you can see all the associated weights with those. So the challenge is picking the right optic and the right sensor for the aircraft that you're designing for. And again, these uncooleds are, they just dominate the market. Thousands and thousands of these are sold around the world every day. That may be an exaggeration. So technology in the long wave market, we've had 17 micron sensors for a long time, and right around the corner coming up are 10 and 12 micron pixels. So 17 micron have, well, okay, first of all, the smaller pixels allow you to design a smaller camera and use less focal length for the same IFOV. So everything helps. If you can generate the same performance with a 10 micron or a 12 micron pixel, you get, it's just better in terms of size, weight, performance versus a 17 micron pixel. So 17 microns have been around for 5 or 6 years. 12 micron first emerged about 3 years ago and are available now. 10 micron should be available around the corner. And the benefit is size and perhaps cost. The example here is that these two cameras have the same performance in terms of horizontal field of view. Both of them have an 18-degree horizontal field of view. The top one is a 17 micron pixel. The bottom one is a 10 micron pixel. So everything adds up in your favor in terms of size, weight with smaller pixels. So for multi-rotors, they're typically fixed focal length. They're very common. Pixel size was 17 microns. It's moving to 10 micron and 12 micron. A typical VGA sensor with a 35 micron has an 18-degree horizontal field of view. You can get a wide range of optics. Typically, the fields of view are 90 degrees to maybe 15 degrees. Those are the practical optics that you can fly on a multi-rotor. Key is knowing the distance to target, the resolution required for your task, and then picking the right lens. Keep in mind, with the uncooled microbolometers, it's basically one lens per camera. You can switch lenses, but it's not ideal. And you change your resolution. The only way, when you have a fixed field of view, the only way to change your resolution is to move closer or further away from the target. So defining resolutions. Certainly there's 60 by 80 and 80 by 80. That's the low resolution class. You can get some good work done with these resolutions, however. Don't discount them. Medium resolution now is 160 by 120 or 320 by 240. Most commonly, we see VGA resolution being 640 by 480, and you can get today 1024 by 768. Around the corner, we expect to see SVGA or SXVGA, I think it's called, which is a 720p or a 1280 by 1024. And very exotically, full HD is very rare but achievable, and that's 1920 by 1200. Frame rates are either 9 hertz, 30 hertz, or 60 hertz. The 9 hertz is an export classification caveat. I won't go any further than that. All the uncooled long wave systems, except for very few and rarely, are rolling readout. And like I said before, the lenses will vary from 90 degrees to 12 degrees horizontal field of view. So for multi-rotor use, here's some beautiful examples. Some examples: search and rescue, electrical inspection, agriculture. You need to pick between thermography and non-thermography. Thermography is temperature measurement. Some applications require thermography. The electrical inspection, for example, requires thermography. Practical systems are available by some manufacturers, most dominantly by FLIR. The one on the right is from Yuntech, a Chinese company, and it ranges from consumer to professional. The FLIR View Pro on the left is just one of the most fantastic infrared cameras you can get. It's very practical, very capable, very elegant, very cost effective. In long wave and for multi-rotors, around the corner, there's going to be higher performance systems. So we've achieved uh, essentially a continuous zoom version that is small enough and light enough to fly on multirotors. So implementing small pixels, 12 microns, new lenses, 15 to 75, and with a wealth of features that make it practical for multirotors. So I don't want to say that multirotors are only fixed field of view. We have multirotors, we have like cameras suitable now for the multirotor class that will offer continuous zoom. And this is just a recent development. So now on to cooled systems. Who would want a cool system? It's expensive. It's got a cooler. And shoot, why would I want a cooler with all these uncooled sensors around? Well, and here's, you can see a couple examples. Again, I go back to this F number issue. You know, these are two 2-degree horizontal field of view, 4,500 grams versus 1,200 grams. You can fly one and you can't fly the other if you need that horizontal field of view. The other benefits are short integration time. With a smaller sensor, there's no payload drag. Your windows are easier. The lenses are more capable on cooled systems. Cooled systems see through the atmosphere especially well. Now, and you just got to ask, you know, can I achieve my goal with a long wave? If you can't, you have to go to midwave. And at some point, you know, the performance of midwave matches up with the performance of the aircraft. Why cheat your aircraft with the limited performance of long wave if the value of the aircraft matches up with the value of a midwave sensor? So some of the advanced payloads that we've dealt with are mostly military, mostly designed to do ISR, intelligence, surveillance, and reconnaissance. Long standoff systems for the law enforcement, manned and unmanned, and then some wide area surveillance. 4-axis stabilization, 15 microradians line of sight, and as you get heavier and heavier, your stabilization gets better and better, mostly due to inertia. Heavy systems, the 100-pounders, have 5 microradians or less line of sight stabilization. So most of them are continuous zoom optics. You know, for the small aircraft, long wave can get down to 6 degrees, midwave can get down to 2 degrees. The advanced payloads are dominated by midwave systems. They're typically fixed wing platforms that have long duration, 12, 24 hours. I mentioned the small tactical air systems, STUAS. And most payloads have multiple channels now, EO, IR. EO is the visible. IR, LB is laser designator, LST is laser spot tractor. The LM is a laser marker, iSafe laser rangefinder. Those are the additional payloads that are going in. And understand that we're dealing with STUAS payloads that weigh about 5.5 kilograms or about 12 pounds. So same, I just brought this one up again just so you understand what kind of AGLs we're dealing with and what kind of aircraft we're dealing with. I don't want to dwell on this again too much. So the thermal imaging requirement for this market, typically the midwave imager dominates the payload. You can see in this example, there's a midwave, that's the big lens right there. The iSafe laser rangefinder is up there, and then there's a visible camera. But that midwave accounts for about 1/2 of the mass, at least, inside that payload. So that's why the thermal imager is so important in midwave, is because it dominates the weight. So where are we going in the future? Everybody wants better resolution, but they want to ensure that we don't get too heavy. So the only way to get better resolution is smaller pixels or more focal length. So you can see up there that we achieve more focal length with a folded telescope, and that's we're using the same pixel size in this case, a 15 micron pixel, but using a folded telescope to get up to 800 millimeters of focal length. So those are the extreme challenges that you have to go through when you're developing a new payload that needs to push the realms of performance. And then the other challenge for us nowadays is to achieve smaller payloads, but with the same resolution, say less than 65 milliradians. So some of these examples are sensors that have come through our shop where we think we can get into a 5.5-inch diameter articulated with 4-axis stabilization. And so we're achieving narrow field of view in the 50 to 60 microradian range and continuous zoom with 10x, and doing at least EO and IR, and then provisions for other payloads, being SWIR or other laser payloads in future developments. So we achieve this with smaller pixels and thus smaller optics. So I just want to pontificate about current state of the art and current state of the shelf. So I've been around this business long enough, and I see state of the art all the time. But the takeaway here is state of the art means, you know, you got to have $1 to $3 million to get it over the hump, and then you got to start paying for productizing it. So beware if someone says state of the art. I don't like that term anymore. I like to use state of the shelf. What can you buy now to develop a payload that you can rely on 2 years from now? You jump into state of the art and you find yourself painted into a corner in terms of technology. So I recommend that everybody understand the state of the shelf, what you can buy now before launching into a payload development. Okay, so I've run on for a long time, and I'd like to say thank you and open it up to questions.
Well, thank you very much, Chris, for that very thorough presentation. And attendees, if you have any questions, now is the time to enter them into the questions box. And while attendees are doing that, I will begin here with the first question. Why, and this came in toward the beginning of your presentation, Chris, why is there a move toward IR heating?
Why is there a move towards IR heating? IR imaging is the imaging of heat. If there is heat, what we are doing is imaging the heating on the ground. So an example of heating would be, say, a solar panel that has shorts in it. It heats up. So we're detecting that short indirectly through the heat that it generates. I hope that answers the question. Why?
Okay. And here is a second question that is not completely, I don't know completely what he's referring to. The question is that similar to FLIR? And I think he is asking, is thermal imaging similar to FLIR?
So FLIR historically is forward-looking infrared. In the 60s, when the first thermal imagers were deployed on aircraft in the Vietnam War, they referred to them as FLIRs. The company FLIR is FLIR Systems, Inc., and they're the largest thermal imaging camera company in the world, great company. And the two are used interchangeably, but the historical context of FLIR goes back to early thermal imaging systems, standing for forward-looking infrared.
Okay, thank you. Can we relate the image to mineral wealth?
So they're referring to using infrared imaging for airborne detection of minerals, and that falls more in the realm of hyperspectral imaging. That is an emerging field. There are specialty applications that use, or specialty systems that use both visible, SWIR, and maybe thermal imaging systems and special processing to measure reflected light and render information about mineral wealth. So that is an application, and it's an indirect way to get wide area information about what the surface chemistry is on the ground. So the answer is yes, broadly speaking.
Okay, thank you. Is there any application for cooled LWIR sensors?
Yes, there is. The cooled long wave can see through smoke, so it's very popular for military battlefield situations. You can get very short integration times, very short exposure times with long wave too. So if you have fast imaging systems or very fast flying systems where motion blur on the ground needs to be minimized, that's the benefit of a long wave cooled system. Long wave cooled is far less common than mid wave cooled, and you suffer optical F number limitations with long wave cooled. And that is a complicated discussion that has to go back to F number and such, because you're practically detecting, call it 8 micron light versus 4 micron light, and there's fundamentals in physics that drive resolution and F number that drives optics development. So yes, there are practical applications for long wave, but they're rare and typically more expensive.
Are you concerned about image resolution in low F number imagers?
No, because the lower the F number, the better the resolution typically. You get better MTF, the lower your MTF modulation transfer function. That's a fundamental measurement of an optic. You get the lower the F number, the better the resolution you get. So that's a fundamental from the optics point of view. As a practical matter, we match the F number to the sensor. So if you have a low F number long wave system, you're getting the best possible resolution if you're running f1.2, f1.4. In a mid-wave systems, you match the F number to the system, and you can get equivalent resolution with F4 systems in mid-wave. So it's not a trade-off. You get to the trade-off when you get to the effective focal length per unit F number.
Okay, thank you. How are calibrations for thermography performed with LWIR systems with adjustable optic/focal lengths?
Generally, they're not. Most thermographically calibrated systems are with a single field of view. I think if you survey the industry, it would be difficult to find continuous zoom or multi-field of view systems that are thermographically calibrated. And it's a complicated discussion as to why this is. Some of the challenges with thermographic calibration is temperature measurement of the lens, because in a long wave system, I don't know what the percentage is. Consider it 99.9% of the radiation that's hitting the sensor comes from the lens. And so you have to know precisely the temperature of the lens. And then when you consider changing that lens during a zoom action or a field of view change action, that imparts uncertainty and difficulties into the calibration process. So the bottom line is that I think, and I'm open to correction here, but there's just not too many systems out there that have variable field of view and thermographic calibration. Most of them are single field of view.
Okay, thank you. Can you explain the difference between thermal imaging cameras and OGI cameras?
So optical gas imaging, that's what OGI stands for. Optical gas imaging is a specialty midwave application that is only now being considered for airborne applications. And OGI has a very narrow spectral bandpass, and the most common would be around the methane absorption line. And that methane absorption line is at around the 3.2, 3.3 micron waveband. And so when you image right on that narrow waveband, you can see concentrations of methane leaking from facilities in natural gas and petrochemical, in a number of energy facilities. And so optical gas imaging in airborne is one of the future applications that we're paying close attention to. And we, in fact, have cameras that address that market currently.
Okay, thank you. I'm going to take one more question here, and that is, have you seen any application of lighter weight polymer opticals with MWIR systems?
No, I haven't. I've seen polymer opticals in a number of systems. Well, in a number of systems, but mostly limited to laboratory applications. So the building of a practical, commercially available polymer optic has not come about yet. And again, I go to that state of the art versus state of the shelf. What can we buy? What can we deploy? I think the benefits of polymer opticals could be much lower cost. And so if we get much lower cost at equivalent performance in midwave, that would be beneficial. But you really need to match the performance, because the cost of a midwave system is so high nowadays that you don't want to throw away performance on a lower cost optic. That's just impractical. Save a few pennies here and you still have an expensive system because of the cooler. Why not, optimize performance per unit cost in that case? So, but it's something we'll certainly see in the future and we'll pay attention to.
Well, thank you very much, Chris. And attendees, at this time, I'm going to close the webinar, but I will be sharing all of your questions and contact information with Chris. So he will have all of your questions. And I would like to thank Sierra Olympic Technologies and our speaker, Chris Johnston, and all of you attendees for joining us today and participating in today's webinar hosted by Photonics Media. Thank you.